Let us now continue with a very important concept which we are going to use in question number 9 and 10. In question number 9, we are going to do the questions from the basic principle. That is, in order to check whether the given function is differentiable or not, we will check by the basic principle. We know that if y equal to fx is a given function, then the derivative dy by dx equal to fx is defined as limit h tending to 0 fx plus h minus fx upon h. Now the given question is fx equal to mod of x minus 1. We have to check the differentiability at x equal to 1. So first of all, it being a modulus function, we need to redefine it. So let's redefine it as fx equal to x minus 1 when x minus 1 is greater than or equal to 0, which means x will be greater than or equal to 1. If it is equal to minus of this, that is minus of x minus 1. If x minus 1 is less than 0, that is x is less than 1. So clearly this function is defined in one manner on the right of 1 and another on the left of 1. And so the derivative would exist only if the left hand derivative is equal to the right hand derivative. Now first of all, let's define the left hand derivative. The left hand derivative at any point x is defined as limit h tending to 0. We give a negative increment, means the value of x is approached from the left. So f of x minus h minus fx upon x minus h minus x, which gives us the left hand derivative as limit h tending to 0 f of x minus h minus fx upon minus h. Now at x equal to 1, the left hand derivative would be limit h tending to 0. In place of x we will write 1. So f1 minus x minus f1 upon minus h. Now on the left of, obviously here if it is 1 minus h, so the function is we will take that function which is on the left of x equal to 1. So and from the definition we know that when x is less than 1, fx is equal to minus x minus 1. So substituting we get limit h tending to 0. We will be using this definition. In this definition we will replace x with 1 minus h. So we get minus of 1 minus h and minus 1 remains as it is, minus. Now at x equal to 1, the value the function is x minus 1. So we have 1 minus 1 upon minus h. This gives us h limit h tending to 0 h upon minus h, which is minus 1. Now let's consider the right hand limit derivative. Right hand derivative is defined as, we are giving a positive increment to x, so it is defined as limit h tending to 0 f of x plus h minus fx over x plus h minus x, which is given as limit h tending to 0 f of x plus h minus fx over h. Now we will check at x equal to 1. Now at x equal to 1, the right hand derivative would be limit h tending to 0. Now in place of x we will write 1. So f of 1 plus h minus f1 upon h. Now on the right of 1 we know that the definition of fx is x minus 1. Substituting we get here, in place of x we will write 1 plus h. So we get 1 plus h minus 1 and minus 1 upon h. This gives you limit h over h, which is 1. Clearly, left hand derivative is not equal to right hand derivative, as left hand derivative is minus 1 and right hand derivative is plus 1. So, the function is not differentiable at x equal to 1. On the same lines, you will do more question. You can do any question of this kind. Now, yet another kind of question is question number 10, which is f(x) is equal to greatest integer function of x, and which is defined from 0 to 3. We have to check whether it is differentiable at x equal to 1 and x equal to 2 or not. Now, we know that a differentiable function is always continuous, that is, a function which is not continuous at a point can't be differentiable. So, such kind of questions can be done using the continuity, because we know that a greatest integer function is not continuous at any of the integral values of x, and in particular at x equal to 1 and x equal to 2. So, since it is not differentiable, it can't it is not continuous, it can't be differentiable also at x equal to 1 and x equal to 2. And we have already discussed the continuity of greatest integer function in one of the previous questions. So, you can write here, you can just show the discontinuity, the procedure of continuity you can check and show that the function is discontinuous at each of the integral points, and that way you can prove this question. Thank you.